Welcome everybody. This is our usual QGASLab strings and fields seminar slot. Today we're very happy to have Adi Armoni, who's a very good friend from Swansea University, who will be talking to us today about a recent PRL paper of his. It's very unusual for string theorists to get PRLs published, so that's great. Fantastic news for Adi, which means also that this result must be important, not only to string theorists but to biologists and social scientists, etc. Okay, so Adi will tell us about the S-dual of Maxwell-Chern-Simons theory in 2+1 dimensions, I'm assuming.
Yes. Thanks, Jeff.
Pleasure.
Thanks for the invitation. And let's see. So indeed, it's based on a recent paper in PRL. And the issue is indeed to find the S-dual of a theory. So let's start with the old S-duality. So when we talk about S-duality, we mean S-duality of two n=4 super Yang-Mills theories. And what it really means in the abelian case is just the old electric magnetic duality that swaps electric and magnetic fields in Maxwell's theory. So that is probably was known, I don't know, probably in the 19th century. So the moment Maxwell published his equations, I guess that people noticed that without sources you can exchange E with B and B with minus E, and the Maxwellian equations are invariant under, in the modern language, F goes to star F. Now in 3D, when we say electric magnetic duality, well, that's a bit strange to say. We can speak about S-duality, and again in the abelian and the, let's say, the bosonic case without supersymmetry, what we observe is that the field strength F is replaced by star d phi, namely that Maxwell theory is equivalent to a theory of a compact scalar, and that's it. Counting the degrees of freedom, it makes sense, and that's it, a free massless scalar. Good, so everything works. But then what happens if we add to Maxwell theory a Chern-Simons term? So what is the S-dual in that case? Now we can, or we naively, we may use S-duality in type 2B string theory to find the answer. So on the left side, we have the electric theory, which is nothing but, a D3 brane suspended between NS and 1, K, the theory that lives on, let me annotate if I can. Can I, or maybe I will use, can either annotate using, can I, let's see, the zoom annotation, or maybe just 1 second. Yeah, so you can see what I'm writing, I guess.
Yes.
So on the electric side, we have here 3D F squared. Oops. But now it doesn't annotate, but that's strange. If it's full screen, I cannot annotate. So we have F squared plus Ka wedge F living on the left brane configuration. And then naively, if we could sort out what is the theory that lives on the S-dual, which is, I mean, to construct the brane configuration is easy. The D3 is replaced by a D3, then S5 by a D5. And then instead of 1, K, we have minus K, 1. So naively, we know what is the S-dual, except that we don't know what is the field theory that lives on the right brane configuration. So then the branes will not help us. On the other end, if and not if, when I will sort out the S-dual of the theory on the left-hand side, it will teach me also something about string theory. It will tell me what is the field theory that lives on a brane configuration that consists of D5 and a tilted minus k, 1 5 brane. So what I will do, and eventually I will derive the S-dual theory using field theory techniques, but it will teach me something about string theory. So that's the idea, to find the S-dual of Maxwell-Chern-Simons and to learn something about string theory as a result. So that's the plan of the talk. Any questions about, that's the introduction part, the goal of my talk. Any questions, please?
So the field theory lives on the intersection of the D5, D3, and 5 brane, right? On the 1, k 5 brane.
So the way to think about it is that the Chern-Simons lives on the intersection of the D3 and the 1, k, or the minus k, 1. So that's the Chern-Simons term. And the Maxwell, on the left-hand brane configuration, the Maxwell theory lives in the bulk. I mean, on the D3 itself. It's just the dimensional reduction from 4D to 3D. So because it's a D3 on a segment, so it's Maxwell theory on a segment with some boundary conditions that reduces F squared from 4D to 3D. And that will be also the idea in field theory. The way I will construct the S-dual is to think about it as a 4-dimensional theory on an interval.
Okay, so what's the role of the D5 or the NS5 in this case?
Oh, it's a boundary condition, because without it, then I will have a 4D theory, but I want to put it on an interval to reduce it to 3D.
Okay, got it.
And eventually I need to take the limit where the interval is very, very small to have a 3D theory. So,
okay, cool.
Okay, so let me proceed. So first of all, let's see let's talk business. So what I'm talking about, what is the Lagrangian of the theory? So this is the Lagrangian. So the first part is the Maxwell part, and then I add to it Chern-Simons term. Now, what is the dynamics of the theory? So it's easy to see. It's a free theory, essentially. So it's just a theory of a vector boson of mass g squared k over 2 pi. So we see that, and that's the theory. So at low energies, much below the mass of g squared k over 2 pi of this vector boson, we almost have nothing. So the infrared of the theory is just the topological Chern-Simons theory. So the full theory is a single vector boson plus a bit of a topological field theory. That's the only thing that remains at low energies, at long distances. Now, because of this term, we will see that we have a ZK one-form symmetry, and we will see that it is generated by, I will derive it by this operator G, which is the exponent of this I integral over, I mean, what's written here. I will derive it. So for the moment, I'm just introducing it to say that there is a ZK one-form symmetry in this theory. And moreover, when the theory is compactified on the torus, this global symmetry, one-form symmetry, is spontaneously broken, and we have K-degenerate vacua. Now, I'm mentioning all that because that will be important when I will discuss in the next slide the previous attempts to find the S-dual. So it's important to know that there is a global ZK one-form symmetry which is spontaneously broken. So obviously the S-dual has to capture these dynamics. And that was overlooked in previous attempts, as we shall see. So again, let me mention previous works. So the most important piece is a work by Deser and Jakiv, and what they argued is that they can find the S-dual, or a theory which is equivalent to Maxwell-Chern-Simons, and they wrote a theory of a massive vector. It's almost the correct answer, but what they wrote is not the full answer, because what they wrote is just a theory of a massive vector without any information about topology. So their theory is a theory which is empty in the infrared. So there is nothing left, and therefore it cannot be the solution of the problem. It cannot be the full solution, and as we shall see, it's part of the solution. Now, another thing which exists in the literature and it is misleading is concerning the Chern-Simons piece. So there is the claim in some papers in the literature that the S-dual of a level K Chern-Simons theory is a level -1/K Chern-Simons theory. Now, again, on the one hand, it's kind of appealing to say, well, the Chern-Simons theory of level K is replaced by -1/K because that's perhaps because of the branes. Once you have a 1, K and you replace it by -K, 1, then you are tempted to think that something happens to the level K Chern-Simons theory. So you're misled by the branes. And it is also kind of, if you think about K as a coupling, then it is tempting to say that S-duality replaces K by -1/K. But that cannot be the answer because it doesn't make sense. A fractional Chern-Simons level is not gauge invariant. So even in the abelian case, when you talk about fractional Chern-Simons term or level in a Chern-Simons theory, that cannot be correct. So there are like several claims in the literature, and all of them are not complete or not correct. Now, one thing which is correct but incomplete is just what happens when a semi-infinite D3 branes intersects or ends on the 1, K 5 brane and the S-dual. So that was done by Gaiotto and Witten, and they found the S-dual of the theory that lives on a D3 and ending on a 1, K. So the S-dual is a D3 ending on a -K, 1. And what they argued is that then this is the partition function, what I wrote below. That's the theory that lives on the intersection. So the S-dual somehow contains two fields. Let's call them A and C. And we have to have both of them. Now, you see, if you naively integrate what is it, C, then you get a level -1/K Chern-Simons term, except that you cannot do that. So the integration, as we shall see, is very tricky. And so what they wrote, the Gaiotto-Witten theory, is correct, and that's the S-dual, but it's not -1/K Chern-Simons theory. So we know like pieces of the solution, which will help us. So we know what happens without the Maxwell part, just Chern-Simons theory. And we have an idea from Deser and Jakiv what should be part of the solution. So let's see what is the full solution. So the idea is to start from 4D electric magnetic duality to review the way it works in 4D, and then to do dimensional reduction and to implement the boundary conditions. So in principle, it's straightforward. So let's see, we start with 4D, and one way of deriving electric magnetic duality in 4D in a full quantum theory, not at the classical level, but in a like proper way, is to start from the following, what we call it, or in the literature, it is called a master partition function. Let's see why it is called a master partition function. So we integrate over what we called Fm, and Fm is gauge invariant to form, and over DAE, and we write this expression in the action. Now, so what we have, the first term is F wedge star F, that's kind of a Maxwell part, and then we have the two form Fm wedge DAE. Now, why do we consider such a partition function? Well, because it's kind of a hybrid of the electric and the magnetic theory. And the reason it's a master partition function, if we integrate over Fm, we get the electric theory, right? Because, well, if we integrate over Fm, what we get is what I wrote below. It's the integration over AE, and the action itself is the 4D Maxwell theory. So the master equation, upon integrating the magnetic two form, leads to the Maxwell theory. Now, if on the other end we integrate over AE, so look at the first line, suppose that now instead of integrating over Fm, we integrate over AE, then what we'll get is the following. So let me explain. Because of the term F wedge DAE, the integration over AE gives me the condition DFM equals 0, namely a delta function. So that's exactly the partition function I wrote now. So we have to integrate the DFM, then we have a delta of D, small d, Fm, and again, the Maxwell theory, but now written in terms of a gauge invariant two form. Now, the condition DFM equals 0 means that, well, it's what we learned in the first year, that when we teach the students that the electric field is the gradient of some potential, it's in differential forms, it's the statement that because DFM is 0, it's kind of a conservative force, that's what we, or conservative field, that's what we tell the students. So in modern language, it means that DFM implies that Fm can be written as DAM. And then writing the partition function in terms of AM, we get the magnetic theory. And the magnetic theory is, again, a Maxwell theory, but this time with a coupling 1 over G instead of G. So what we learn is from this exercise is that we can recover electric magnetic theory starting from a master, this master partition function. And in principle, all we need to do is to use this master partition function and to do dimensional reduction to 3D. So this is a 4D theory. All we need to do is to do dimensional reduction to 3D. And that's, of course, also the intuition comes from the story with the brains. We have a D3 suspended between two 5 brains. So it's a 3D, it's the 4D Maxwell theory on an interval with a certain boundary conditions. So that's what we need to do. So let me do that. Now, what we have is Fm wedge DAE, right? So we have an interaction between Fm and AE, and we have to reduce the 4D two form to 3D. Now, when we do the dimensional reduction from 4D to 3D, the 4D two form becomes a 3D two form Fm, and an additional one form AM. Now, FM and AM are both gauge invariant. So AM is not a gauge field, it's a one form, it's a vector, but it is gauge invariant. So it's important to remember that when we reduce the 4D master field to 3D, AM is not a gauge field, it's gauge invariant. Now, the 4D gauge field AE becomes a 3D gauge field AE, small AE, and a scalar phi. So what do we have upon reduction to 3D? We have 3D two-form FM and a one-form AM. And in addition, we have a one-form AE and a scalar zero-form phi E. Now, it turns out I didn't write it, but there are like two things that decouple from each other. There is AM and AE that interact with each other, and there is FM and phi E that also interacted with each other, but not with the rest. So the 4D upon reduction from 4D to 3D, the 3D partition function becomes kind of two partition functions that do not interact with each other. It factorizes to a product of two partition functions, and they imply two dualities. One duality is the duality between phi E and FM, and that's the old duality that we know that leads to the well-known duality between Maxwell theory and free scalar. That's not interesting. I could have written it down. Maybe it could have saved me like 3 minutes of speaking. But what is interesting is the other duality between AM and AE. And what's written in the middle of this page is the starting point of the duality. So that's my proposal. That's a master partition function. So let's see what do we have in this partition function. So we have AM and AE. Both are one forms. AM is gauge invariant one form, and AE is a gauge field. So the first term obtained from the dimensional reduction of capital FM is, we see what it is. We have minus G squared, AM wedge star AM. So it looks like it is not gauge invariant, but no worries because AM itself is gauge invariant. So it is a proper gauge invariant term. And then we have an interaction term between AM and AE. So we have AM wedge DAE. And finally, let me add the Chern-Simons term for AE. So that's my starting point. Now, I could have started my talk with this partition function without motivating it and saying, okay, let's start with this partition function. Let's see what happens if we integrate either over AE or AM. So let's see. If we integrate over AM, it's an easy integration, and we get the electric theory. So indeed, upon integrating AM, what we get is the first term is the Maxwell theory in 3D, and the second term is the Chern-Simons. So using this master partition function, upon integrating AM, I found Maxwell-Chern-Simons theory. So what we expect is that when we integrate over AM, we'll get AE, we'll get the dual theory, the S-dual. So before doing that, any question? Okay, so let me proceed. So let me mention how like this master partition function and how it relates to previous proposals and previous results. So let's do the following. First of all, let's consider k equals 0, namely, let's omit the Chern-Simons term. Then what is left is what's written in the top, this partition function. Simply, I omitted the Chern-Simons term. Then, if we integrate AE, what we get is that dAm is 0, namely, AM can be written as d phi. So then what we get is a partition function of a free scalar. So that means that the dual of Maxwell theory without a Chern-Simons term is a free scalar. So that's good. So the master partition function for k equals 0 make sense. And the other case is what happens when g squared is 0, namely what happens if I'll omit the Maxwell term from the master partition function. And then what we see is that we get the following partition function, dAm, dAe, and then the first term is AM wedge dAe, and the second term is the Chern-Simons term. And this is exactly the Gayotto-Witten partition function. So I managed to recover in two limiting cases well-known results, the dual of Maxwell theory without Chern-Simons and the dual of Chern-Simons without Maxwell. So it makes sense, at least the two limiting cases work. And now let's see the full solution. So the full solution is as follows. What we need to do, we need to take the master partition function and integrate over AE. But that's that's not an easy task, but there is a trick, and the trick is to change variables. Let me show you the master partition function. So that's the master partition function. And what we see is that we have an interaction term between AM and dAe. But we can decouple AM and AE by a simple change of variables. And that's what I did. If we do this change of variables, namely we introduce B instead of AE, then essentially it's like diagonalizing or like decoupling the two fields. And that's the partition function that I get. So the partition function after a change of variables is dAm dB. AM is gauge invariant one form. B is gauge field. Now they decouple. And what we have is two actions. The first action is the Desert-Jakiv action. It is a theory of a gauge invariant one form. It describes a massive vector of mass g squared k over 2 pi, what they called capital M. So that's the first theory. And then there is another piece, and they don't talk to each other. The other piece is just a level k Chern-Simons theory. So what we have is that the claim that I wish to make is that the partition function of Maxwell-Chern-Simons is equivalent, is equals to the product of two partition functions, the partition function of Desert-Jakiv times the level k pure Chern-Simons theory. So that's the claim, that's the S-duality claim. And now let's see whether it makes sense. So as I said, well, let's see what's the dynamics of this theory. So one thing that we see is that it's a theory of a massive vector. That was also already shown by Desert and Jakiv. At low energies, we expect a topological quantum field theory, and that's given by the field B. So what we see is that S-duality consists of kind of two theories. One, which is a term which is a vector, gauge invariant vector. And the second term is like sort of singlet of S-duality. So the Chern-Simons goes to Chern-Simons. So the topological part is intact. Now, it should be, because when we start with Maxwell-Chern-Simons, we know that at lower energies, there is a Chern-Simons term, a level K Chern-Simons term. So it makes sense that the S-dual will contain the same term. And that's what we get. Right. Let me write the explicit map between the two theories. So using the equations of motion for the master field, I can essentially write the dictionary. So what is the relation between the magnetic and the electric variables? So given AE, the variable of the electric theory, I can write down AM and B. So given the information about the electric theory, I know what is AM and what is B, what are the variables, what is the relation between the electric and magnetic theory. So, and vice versa, or conversely, given AE, given B and AM, I can write what AE is. So essentially, I know now the explicit map between the two theories, which is very nice. So I know the relation between the electric and the magnetic theories. And now I learned something about string theory. So now I know what is the theory that lives on the right brain configuration. And essentially, that was also a mystery. And there are many papers about the right brain configuration, but somewhat, how to say, not correct. So there are various statements about what lives on the right brain configuration, and some partial answers are correct. For example, Gayotto and Witten. If you take the D5 away, that's Gayotto-Witten theory, and that's correct. If we have k equals 0, then we know the answer. The right brain configuration is two parallel D5s and the D3 suspended between them, and that's the original Hanani-Witten paper, and it's also correct. But the general solution and the statements in the literature, but the general solution were incorrect. And so now we know what is the theory that lives on the right brain configuration. So in the rest of the talk, I would like to discuss the dynamics of both theories and to show you that the solution makes sense in terms of not only at the level of the partition function, but also in the level of observables, and then I will speak also about generalizations. So are there any questions?
Yes, I have one. So the Maxwell-Chern-Simons is not supersymmetric. So the S-duality that you're talking about is a non-supersymmetric duality, right?
It's the bosonic piece. Yeah.
Right. Is this related in the brain configuration to the fact that this second 5 brain is tilted? That breaks the supersymmetry, doesn't it?
No. Well, with the tilting, so okay, good, very good. So that very good. So we can tilt we can construct a brain configuration that preserves n equal 2, n equal 1, or n equal 0, depending on the tilting. But we can still tilt the other 5 brain in a way that we retain a certain amount of supersymmetry. Now, if we tilt it in a brutal way, we break supersymmetry completely. So there are two ways of to think about the S-duality that I either the bosonic piece of the supersymmetric theory, because at the very end, everything is in the adjoint. So we'll have several pieces that do not interact with each other. Everything is in the adjoint. So there will be, in the supersymmetric theory, consists of the bosonic piece I'm talking about and extra stuff, but they don't interact with each other. So we can either think about what I'm presenting is the bosonic piece of the full supersymmetric case, or that I'm considering the tilting in a way that I break supersymmetry completely. So there are two ways of thinking about it. But in principle, I should be able to write the full supersymmetric S-duality, except that I didn't really do that. So I didn't bother to do that. But that should be, I should be able to do it, to complete it.
Great, thanks.
Okay, so let me proceed. So now I would like to come back to the issue of the ZK, the one-form symmetry. So I'd like to consider the generator of this symmetry. So I want to define an object G such that when I act on a Wilson loop, it essentially tells me the nullity, not the nullity, the k-ality, or how many kind of fundamental strings goes through a certain contour or intersects a disk, which is the shaded area, intersects this disk whose boundary is the contour C. So essentially, if this string that intersects the disk is the fundamental string, I can think about either one string which is a bound state of several fundamental strings, or I can consider like intersection of multiple fundamental strings, and they have some charge, so which is the number of fundamental strings that intersect this disk. So I want to count this charge, and the operator that I want to construct, called G, when it acts on this Wilson loop or a string, just counts the number n, the number of fundamental strings, and the eigenvalue is this exponent of I 2 pi n over k. So so we say that there is a zk charge, and the Wilson loop carries this charge, and I want to count the total charge. So so another way of saying it is that the Wilson loop is written as an exponent of in the integral of AE, and I just want to count this n to be able to extract the small n from the Wilson loop using some operator G. So let me construct it. So keep in mind this setup, that there is a disk D, and there are like strings intersecting this disk, and there is a contour C whose the boundary of this disk. So it's not so difficult to define this G. First of all, what I'm using is just the equation of motion of the electric theory. So this is the equation of motion of Maxwell-Chern-Simons. D of this object is small j, it's a current, and I'm writing small j as d of capital J. So capital J is the integral of this electric current, small j, over the disk D. So now I can integrate both sides. I have a derivative on both sides. So I get the equation in the middle of the page. And I have this capital G. Now I can define the generator. So the object, the generator G, is the exponent of I 2 pi over K of this integral over the contour of the object that I wrote here. And somewhat surprisingly, or maybe not, it turns out that this object that I propose, that is the generator of the ZK in this theory, turns out to be the exponent in the magnetic theory, turns out to be the exponent of just the integral of the contour C of B. So we see the advantage of the magnetic theory. In the S-dual, we had two fields, a gauge invariant AM and B. AM doesn't appear at all. And it's intuitive because AM doesn't know about topology, about Chern-Simons, about ZK. The AM is just a vector, a gauge invariant vector, something that describes the massive piece of the theory and doesn't know anything about the topology. So if we want to consider the generator of the ZK, it's not surprising that starting from the Maxwell theory, we ended up in the dual, the S-dual, with something that contains only B. So that's kind of nice, this feature. And it shows you the advantage of using the S-dual. Right, what else I'd like to mention, how they map to under S-duality. So what is the Wilson loop? The Wilson loop is the Wilson loop in the electric theory is the exponent of the integral of AE, and that's the fundamental string. We expect it to be, let's say in string theory, an F1 to be mapped to a D1. So we are interested in knowing what is the object in the magnetic theory, and using the explicit map, we find this object that I think appeared already in the literature. So it's a combination of both B and AM. So what is the relation to string theory? So as I said, I mentioned Wilson loops can be realized by fundamental strings. So if we look at this set of cartoons, the left upper cartoon, we see F1 and anti-F1 ending on the D3 brane. So we can think about the end of the F1 as a charge. So we see an electric charge Q, let's say, and the anti-charge minus K and minus Q and minus Q, so like in a Coulomb interaction between them. So that's the Wilson loop. So the Wilson loop, or rectangular Wilson loop, can be described by F1 anti-F1. It's just a charge anti-charge in the whole volume of the theory. Now under S-duality, we know that F1 goes to D1 and F1 bar goes to D1 bar. So now I can describe what is the magnetic loop, or a loop made of magnetic charges, the endpoints of the D1 and the anti-D1. So the map, the explicit map, also tells me about what happens with this object in string theory. Now, similarly, I can start, and that's the left bottom cartoon. What happens if I put D1, D1 bar in the electric theory, and what happened to it in the magnetic theory? In the magnetic theory, it will be F1, F1 bar, and that's the right bottom cartoon. So let's discuss this object. Let's ask what happens if we start with a magnetic loop in the electric theory, which maps to some sort of an electric loop in the magnetic theory. So let's see. So it's interesting that it was already discussed in the literature. It was constructed, the magnetic loop in Maxwell-Chern-Simons, and it is mapped to electric loop in the magnetic side, but in the magnetic side, it's again it's made of pure B. Now, one can show, and that was shown by Itzhaki, is that in the electric side, the magnetic loop is trivial. It's just a trivial operator. And it is mapped in the electric to an electric loop in the magnetic side, which is also trivial. Now, you can show that it's trivial using field theory techniques. It's easy to understand why it's trivial in the magnetic side. In the magnetic side, we have K in front of the B. So if previously we had the operator G, this is G to the power of K. But G was something that measured ZK charge. If you take it to the kth power, it becomes a singlet. It is really a trivial operator. So again, the magnetic side is useful. Itzhaki managed to show it also in the electric side. He showed that this object is trivial. Now, it's actually easy to see that both these objects are trivial in string theory. So let me show it and let me annotate. Let's see if which way to annotate. Can I annotate using the, oh, I think I cannot annotate using the Zoom. So let me do the following. Let me annotate this way. So I want to claim that the rectangular magnetic loop in the electric theory, namely this thing, is trivial. And the reason is as follows. Suppose that I consider D1 and D1 bar far away from each other. So in order to reduce the energy, they can simply end on the NS5 brane. So a D1 can end on an NS5 brane. So both can end on an NS5 brane instead of the world volume. And in this way, they reduce the energy. So in the world volume, I will see nothing. It's absolutely trivial. And the same statement is true in the magnetic side. The fundamental string can end on a D5 and also the anti-fundamental string. So instead of ending on the D3, dynamically, they will prefer to end on the D5 to reduce the energy. So we see why these objects are an intuitive way to see why these objects are trivial. Right, I don't have much time, but I think that I'm almost done. So a few comments about generalizations. Suppose that instead of discussing just Maxwell-Chern-Simons, I want to discuss QED-Chern-Simons. So to add the quarks and let them interact with a gauge field. So the partition function, after integrating over the fermions, consists of this determinant. So the determinant of the Dirac operator. So a Dirac field coupled to a gauge field. But because I know the explicit map between the electric variables and the magnetic variables, I can simply, instead of AM, sorry, I should have written here AE. It's not AM, it's AE in the top line. I can replace AE by AM and B. And using that, I can integrate back and write the magnetic partition function. So the magnetic theory will be the previous magnetic theory plus magnetic quarks coupled to both B and AM, as written in the last line of this slide. So I know how to couple matter in the electric side and what happens to it in the magnetic side. And that's non-trivial because, well, it's not anymore just, Maxwell-Chern-Simons, which is a quadratic theory. It's kind of a simple theory. Now it's a theory with quarks that interact. So that's one comment. And another comment is whether I can generalize it to the non-abelian case. So let's try. So let me try to construct the partition function, the master partition function in the non-abelian case. So what I want is something that upon integrating AM, I will get the Yang-Mills-Chern-Simons theory. So a level K Yang-Mills-Chern-Simons theory. And then upon integrating AE, I should get the S-dual. So let's see. So I propose to start with the following action. And you see, so the first term is the same as in the abelian case. The second term is a bit more involved because what I want to get the Yang-Mills theory upon integrating over AM. So what I'm doing, I'm writing instead of DAE, I'm adding to it AE wedge AE. And indeed, we see that if we integrate AM, we get the Yang-Mills piece from that. And then the rest of what's written in this line is the level K Chern-Simons term in the non-abelian case. Now, if I want to sort out what is the S-dual, then I should integrate out AE. So again, it's difficult, but I will use the same change of variables as previously. And what we get, again, is a theory of a massive vector. And then there is a Chern-Simons term, so it's almost identical, but with one crucial difference. This time, there's no decoupling, but B and AM couple to each other in a non-trivial way, which I didn't write all the terms explicitly. So that's about the generalization to the non-abelian case. But and then I on the way I learned something about the dynamics of Yang-Mills-Chern-Simons, that indeed there is a massive vector, there is a topological piece, but they also interact with each other. So that's the dynamics. Right. So I'm finishing on time. That's great. And this is the conclusion. The conclusion is that the solution of the mystery is that the S-dual of Maxwell-Chern-Simons is the Zerjakiv theory accompanied by a pure topological quantum field theory. And then the dynamics of both sides is identical. It's a massive vector and a decoupled Chern-Simons theory. And moreover, at very low energies, what we have is a ZK symmetry, which is spontaneously broken and resulting in K vacua, and that's manifest in both theories. So thank you.
Thanks very much, Adi. Any questions? If not, I have some. Actually, I have lots, but we should probably have this conversation over a drink at some point. So, firstly, do you know what happens if you if there's a difference between coupling scalar matter or fermionic matter to the theory?
So what I actually I think it will be the same, namely, let's go back. I can do the same trick. The issue is that I know the explicit map, and because of that, I'm able to find the dual theory. So even if I couple scalars, because I know how scalars couple to the gauge field, and what happens to the gauge field under the duality, then I can do it. It's
I guess what I'm asking is
to...
if I can incorporate this clarification of Maxwell-Chern-Simons S-duality into the 3D duality web. So for example, if I add scalars to, if I add for example, a Wilson-Fisher scalar, then I can make a vortex. Then I have something like particle vortex duality, except with the vortices being Maxwell-Chern-Simons vortices.
Right. So I think you can. So that's kind of. So I think that all the dualities that people, or most of the dualities people consider so far in the literature are related actually to Seiberg dualities. So they're kind of generalization of level rank, and level rank is Seiberg duality. This S-duality will add another layer. So let me go back to the brains. If we look at this slide and we start from the top left, that's the Maxwell-Chern-Simons, we can exchange the two fibrils that gives Seiberg duality, but that's not what I'm discussing, what I discuss in this paper. But we can first swap the fibrils, get the Seiberg dual, and then we can act with a S-dual, or vice versa. The order doesn't matter. But yeah, we can extend the web of dualities by acting on both sides of the duality you propose with the S-dual.
Right.
So
So
we can do both Seiberg duality and S-duality, or particle vortex, and then act on each side with S-duality. So that will give that's interesting, because I don't know what is I don't know what will happen. So,
but I mean, when I read your paper, one of the things that occurred to me is that there could be something like an S-dual of the whole full 3D duality web.
Yes. Yeah,
that would be interesting.
Doable. I think, yeah, it's doable. I think it can. Probably, well, in the abelian case, it's probably straightforward. I don't think it's too difficult.
Right.
The only thing that I must emphasize is that when I say that I can, that I can do the fermions, you see, I use the map without the fermions. So it's kind of without back reacting. So I don't modify the map. I use the map without the fermions so it's kind of, what is it, like quenched, or it's okay, but we should be aware of that it's without back reaction. So
sure.
But maybe it works in the sense that maybe it's not needed. I'm a bit confused, I must say, about that. Because it's like an exact map, and so I can just like plug it in this action on the top and see what I get. And what I get is what I get. I think that I get the bottom. So I think that it kind of works.
Yeah, it looks like it should work. I can't see any obstruction to it.
Yeah, it looks that it works.
Okay, great. Yeah, we should maybe talk a little bit more about that if you want. Any other questions? Okay, if not, thank you, Adi. It was a really nice talk. I quite appreciated it. I'll send you the link to the video once it's available on YouTube.
Oh, excellent. Thanks.
Fantastic.
Okay.
Thanks. Bye-bye.
Bye.